Welcome to this presentation. Today, let's have an insight of wireless LAN. Wireless communication is one of the fastest growing technologies. The demand for connecting devices without the use of cables is increasing everywhere. Wireless LANs can be found on college campuses, office buildings, and in many public areas. Now, in this model, let us concentrate on two promising wireless technologies for LAN. One is IEEE 802.11 wireless LAN and sometimes called as wireless Ethernet, and Bluetooth, a technology for small wireless LANs. IEEE has defined the specifications for wireless LAN called IEEE 802.11, which covers the physical and data link layer. And other is personal wireless LAN, Bluetooth. Now let's see the architecture of LANs, isolated LANs and versus wireless LANs. The standard defines two kinds of services: the basic service set, that is BSS, and the extended service set, ESS, right? And IEEE 802.11 defines the BSS as the building block of the wireless LAN. A basic service set is made of stationary or mobile wireless stations and an optional central base station known as access point. And now let's see the two sets in this standard. The BSS without an AAP is a standalone network and cannot send data to other BSS. It is called an ad hoc architecture. So in this architecture, stations can form a network without the need of an AAP. They can locate one another and agree to be a part of BSS. A BSS with an AAP is sometimes referred to as an infrastructure network. An extended service set, that is ESS, is made up of two or more BSS with AAP. So in this case, BSS are connected through a distribution system, which is usually a wired LAN. The distribution system connects the AAPs in the BSS. IEEE 802.11 doesn't restrict the distribution system. It can be any IEEE LAN such as Ethernet. And you can notice that the extended service set uses the two types of stations, mobile and stationary. The mobile stations are normal inside a BSS. The stations are AP stations that are part of wired LAN. Now let's see the ESS. When BSS are connected, the stations within a reach of one another can communicate with the use of an AP, and however communication between two stations in two different BSS usually occurs via 2 AP. So the idea is similar to communication in a cellular network if we consider each BSS to be a cell and each AP to be a base station. And you can notice that the mobile station can belong to more than one BSS at the same time. The IEEE 802.11 defines three types of stations based on their mobility. That is no transition, BSS transition, and ESS transition mobility. A station with no transition mobility is either stationary or moving only inside a BSS. A station with BSS transition mobility can move from one BSS to another, but the movement is consigned inside one ESS. A station with ESS transition mobility can move from one ESS to another. However, IEEE 802.11 doesn't guarantee that communication is continuous during the move. And IEEE 802.11 defines two MAC sublayers, that is DCF and PCF, distributed coordination function and point coordination function. And now let's see the relationship between the two MAC sublayers, the LLC sublayer and the physical layer. The physical layer implementation will be seen here. Now the distributed coordination function is the one of the two protocols defined by IEEE at the MAC sublayer is the DCF. DCF uses CSMA-CA as the access method. So wireless LANs cannot implement CSMA-CD for three reasons. One is for collision detection, a station must be able to send data and receive collision signals at the same time. This can mean costly stations and increased bandwidth requirements. Collisions may not be detected because of hidden station problem, and the distance between stations can be great. Signal fading could prevent a station at one end from hearing a collision at the other end. Now let's see the physical process flowchart also. So before sending a frame, the source station senses the medium by checking the energy level at the carrier frequency. The channel uses a persistent strategy with back off until the channel is idle. And after the station is found to be idle, the station waits for a period of time called the DIFS, that is distributed interframe space. Then the station sends a control frame called the request to send RTS. After receiving the RTS and waiting for a period of time called SIFS, that is short interframe space, the destination station sends a control frame called the clear to send to the source station. The control frame indicates that the destination station is ready to receive data. The source station sends data after waiting an amount of time equal to SIFS. The destination station, after waiting an amount of time called SIFS, sends an acknowledgement to show that the frame has been received. Acknowledgement is needed in this protocol because the station doesn't have any means to check for the successful arrival of its data at the destination. On the other hand, the lack of collision in CSMACD is a kind of indication to the source that data have arrived. How do other stations differ sending their data if one station acquires success? In other words, how is the collision avoidance aspect of this protocol accomplished? The key is a feature called NAV. When a station sends an RTS frame, it includes the duration of the time that it needs to occupy the channel. The stations that are affected by this transmission creates a timer called network allocation vector that shows how much time must pass before these stations are allowed to check on the channel for idleness. Each time a station accesses the system and sends a RTS frame, other stations start their NAV. In other words, each station before sensing the physical medium to see if it is idle, first checks its NAV to see if it has expired. What happens if there is collision during the time when the RTS or CTS control frames are transition, often called handshaking period? And now let's see about the hidden station and exposed station problem. This diagram shows an example of hidden station problem. Station B has a transmission range shown by the left oval, that is in this sphere. Sphere in this space. Every station in this range can hear any signal transmitted by station B. Station C, a transmission range shown by right oval, that is in this diagram. This one. Every station located in this range can hear any signal transmitted by C. Right. So station C is outside the transmission range of B. Likewise, station B is outside the transmission range of C. Station A, however, is in the area covered by both B and C. It can hear any signal transmitted by B or C. You can assume that station B is sending data to station A now, right? So, in the middle of this transmission, station C also has data to send to station A. However, station C is out of B's range and the transmissions from B cannot reach C. So therefore, C thinks that the medium is free. So, station C sends its data to A, which results in collision at A because this station is receiving data from both B and C. So in this case, we say that station B and C are hidden from each other with respect to A. Hidden stations can reduce the capacity of the network because the possibility of collision. The solution to this hidden station problem is the use of handshake frames, that is RTS and CTS. So RTS message from B reaches A but not C. However, because both B and C are within the range of A, the CTS message, which contains the duration of data transmission from B to A, reaches C. Station C knows that some hidden station is using the channel and refrains from transmitting until the duration is over. And let's move on to exposed station problem. Now consider the situation that the inverse of the previous one, that is the exposed station problem. In this problem, a station refrains from using a channel when it is in fact available. Station A is transmitting to station B. and station C has some data to send to station D, which can be sent without interfering with the transmission from A to B. However, station C is exposed to transmission from A. It hears what A is sending and thus refrains from sending. In other words, C is too conservative and wastes the capacity of the channel. Now, the handshaking messages, that is RTS and CTS, cannot help in this case, despite what you might think. Station C hears RTS from A but doesn't hear CTS from B, as you can see in this diagram. So station C, after hearing the RTS from A, can wait for a time so that CTS from B reaches A. It then sends RTS to D to show that it needs to communicate with D. Both stations B and A may hear this RTS, but station A is sending state, not the receiving state. Station B, however, responds with a CTS. The problem is here. If the station A has started sending its data, station C cannot hear the CTS from station D because of the collision. It cannot send its data to D. It remains exposed until A finishes sending its data, as you can see here. Thank you.